This is the fourth video of chapter 20 of the Crystal Clear Electronics video series. This time we are going to build a current source from discrete elements. Szabolcs, would you explain to us what a current source is?
Of course! In the previous videos, we explored circuits that produce a constant voltage at their output, so they worked like a voltage source. There are many times when you want to limit the output current in power supplies. You could say that at a specific load current value, you want to switch from voltage generator mode to current generator mode. The operation of current limiters and the current sources are very similar. In both cases, it is a circuit that keeps the current at a fixed value. In different fields of application, users have different goals in mind, hence the two names. The current limiter is protecting against the overloading of a voltage source, while the current source is used to provide the circuit a constant current. An example of such a device could be an LED. The figure shows one of the simplest LED drivers using a current source. This circuit is capable of driving LEDs requiring higher power, but we will stick to low current regular LEDs for now. To build the circuit, you need one NPN transistor, one LED, two diodes, two 100 ohm resistors, one 1 kilo ohm resistor, and one 680 kilo ohm resistor. The two diodes are used to provide a near constant voltage of 1.4 volts between the transistor's base and ground. Since the base emitter voltage drop is about 0.7 volts, the remaining 0.7 volts will drop on the resistor R2. Let's now drive a 15 mA current through the LED in this example. The required resistance value is calculated by dividing 0.7 volts by 15 mA. This gives us approximately 47 ohms.
Unfortunately, we don't have such a resistor, but instead we can use two 100 ohm resistors connected in parallel, as their equivalent resistance is 50 ohms.
The next step is to define the resistance R1. First, find the transistor's current gain in the datasheet. This is at least 200 in case of the BC546BTA, so to get a collector current of 15 mA, the base current must be 15 mA divided by 200, or about 0.07 mA. The diodes need an additional 1.3 mA to produce the expected voltage drop accurately, at least according to their datasheet. Suppose we want to run our generator from 12 volts. In this case, the required resistance R1 is 12 volts minus 2 times 0.7 volts divided by 1.37 milliamps, that is 7.74 kiloohms. It is clear that the base current of the transistor is negligible compared to the current of the diodes. In fact, the transistor gain can be rated anywhere between 200 to 450, depending on which transistor you get from the manufacturer. So we can expect an even lower base current than the calculated 70 microamps. It follows that by choosing resistor R1, we significantly influence the current flowing through the diodes and hence the voltage across them. If 1 to 2 milliamps is already flowing through the diodes, we will reach a voltage drop of 0.7 volt across them. Increasing the current by a few more milliamps will only change their voltage by a few tenths of volts. It means that we can deviate a little from the calculated value of R1, the circuit will work fine anyway.
We have now connected a 1 kilo ohm and a 6.8 kilo ohm resistor in this circuit. The result of this is 7.8 kilo ohm since they are connected in series.
Let's see how the circuit works in practice. In front of us, on the breadboard, we have the assembled circuit. The lab power supply provides 12 volts. With this multimeter, we will measure the current drawn by the circuit in current measurement mode. More precisely, the load current flowing through the LED. You can see this here on the laptop screen. The LED hasn't lit yet because we have to connect the current meter to the circuit. I'll do that now. And then, you can see about 15 milliamps as we planned. In reality, this is only around 12. In fact, it seems to increase a little after the circuit is switched on. The reason for this deviation is that these diodes don't have a forward voltage of exactly 0.7 volts, but somewhere between 0.6 and 0.7, and it is also very temperature dependent. Therefore, we calculate the current variation caused by this diode voltage variation. Because of the 50 ohm resistor, if the voltage drop across the diode changes by 100 millivolts, the current at the output will change by 2 milliamps. So that's why we're measuring a slightly lower current value here. However, something else could be tested. For example, what happens if I set R1 to a value other than 7.8 kilo ohms? Well, now I'm going to remove this 1 kilo ohm series resistor and replace it with basically one wire, so the resulting resistance will be only 6.8 kilo ohms. You can see that we get around 12 milliamps, about the same as before. So it doesn't make much difference whether or not we replace R1 with a slightly different resistor. Now, I'll put the 1 kilo ohm resistor back again. Perhaps something else could be tried. For example, I could connect two LEDs in series instead of one. I can do this by having two LEDs in series here and just switching the current meter. Now you can see that both LEDs are on and the current is still at this 12 milliampere value. Of course, you can connect an infinite number of LEDs in series, since the sum of the voltages across the load, the 50 ohm resistors, and the transistor's collector-emitter voltage cannot be higher than the supply voltage. In other words, the circuit can only maintain the desired current value as long as the transistor voltage is higher than its saturation voltage, which for this transistor is around 1 volt.
So, as a rule of thumb, the supply voltage should always be slightly higher than the voltage across the load.
That's right. In the case of a constant current source, the transistor plays the role of a variable resistor that changes its resistance depending on the voltage drop on it, so that the current flowing through it remains constant. We can even try this and measure it with other input voltages. It is important to note that in such a case, significant power is dissipated on the transistor. Therefore, the maximum heat transfer capability of the transistor must be taken into account when designing.
I seem to have run out of demos on my breadboard.
I think so. You know what it means.
It means that we are coming to the very end of the chapter. We hope you found these few videos to be of use and that you will be able to use them in all kinds of projects. You can find the written curriculum and all the necessary information and links below the video. Follow us on Facebook for the latest news. I hope to see you soon in the upcoming videos. Bye!
Bye!